So in multivariable calculus, we're always building on what we already know, right? Today, we're going to take that a step further and look at higher order partial derivatives, which brings up a really interesting question.
Here it is, the big question for today. When you're taking derivatives of derivatives, does the order you do it in actually change the answer? I mean, if you've got a function with both x and y, is going x then y the same as going y then x? It seems like it should be, but is it? Let's find out.
All right, here's our game plan. We'll kick things off by connecting this to stuff you already know. Then we'll map out all the possibilities. After that, the big reveal, a massive shortcut. We'll put it all into practice with some examples, and then, just for fun, we'll go one level deeper.
Okay, so first up, a new derivative dimension. Before we jump into the deep end, let's connect this all back to something familiar from single variable calculus.
You remember back in Calc 1, right? The second derivative, f double prime, told you all about a curve's concavity, whether it was curving up or curving down. Well, second partial derivatives are kind of like that, but for the big leagues, 3D surfaces. They give us this incredible way to describe the curvature of, say, a hill or a valley on a 3D graph.
Now, to actually talk about this 3D curvature, we need some new language, some new notation. So let's get into it and map out all the different ways we can take these second partials.
So for a function of two variables, let's say x and y, you've basically got four paths you can take. You can go x, then x again, which we call f sub x. Easy enough. You can go y, then y again, f sub y. But then you've got the really interesting ones, the ones we're here for, differentiating with respect to x first, then y, which we call f sub xy, and its partner going y first, then x, or f sub yx.
And these two, f sub xy and f sub yx, they get a special name. We call them the mixed partials. This is the absolute heart of the question we asked at the very beginning. Are they the same thing? Does the path you take even matter?
A really cool way to picture this is to think of a derivative tree. Your original function, f of x comma y, that's the trunk. From there, you get your first two big branches, the first partials, f sub x and f sub y. And then each of those branches splits again, giving you a total of 4 branches at this second level.
All right, and now the moment you've been waiting for. The big reveal. The answer to our whole question comes from this just beautiful and honestly super useful theorem. It's called Clairaut's theorem.
So here it is, Clairaut's theorem. It says that if those two mixed partials we were just talking about, fxy and fyx, are continuous, and let's be real, for most functions you're going to see in your calculus class, they will be, then they are equal. They are the exact same thing.
So what's the big idea here? It's simple. For almost every function you're going to work with, polynomials, trig functions, you name it, the order of differentiation just doesn't matter. This is huge. It's a massive shortcut you can use.
Okay, theory is one thing, but seeing is believing, right? Let's put this theory into practice and actually watch this symmetry in action with a couple of worked examples.
Let's start with a nice, simple polynomial. First, let's find the partial with respect to x. That gives us f sub x equals 3x squared minus 5y. Got it? Okay, now we take that result and differentiate it with respect to y to get f sub xy. Well, the derivative of 3x squared with respect to y is 0, and the derivative of negative 5y is just negative 5. All right, hold that thought. Now let's go the other way. Start with the partial with respect to y. F sub y is 4y cubed minus 5x. Now, differentiate that with respect to x. The 4y cubed part is 0, and the derivative of negative 5x is, yep, you guessed it, negative 5. Boom, they match. The theorem holds. Okay, that was a pretty good warm-up. But what about something a little trickier? Something with some trig, some multiplication, something where it's actually easy to make a mistake. Let's try a function that's going to force us to use the product rule. So check this out. You can see the two paths side by side. Look at the left path. We go x first, then y. Now when we do that second derivative, notice that term, y times cos of xy. Uh-oh. To differentiate that with respect to y, you absolutely have to use the product rule. And that is a classic spot where people make mistakes. Now look at the right path. Same story. When you differentiate with respect to x, you hit that x times cos of xy term, and bam, product rule again. But here's the magic. Even with all that messy calculation, look at the final answers. They are identical. It works every time.
So we've pretty much proven that order doesn't matter for second-order partials. But does this amazing pattern keep going? What if we wanted to go one level deeper to a third-order derivative?
Let's try to find f sub xy(x). It sounds intimidating, but it's just one step at a time. First, we find the partial with respect to x. That gives us y times e to the xy. No problem. Next, we differentiate that with respect to y. And wait a minute, we've got a y in front and a y in the exponent. That's a product of two functions of y. We need the product rule. Okay, we do that calculation and we get the expression in step 2. We're not done yet. Finally, we take that whole thing and differentiate it with respect to x. And you know what? There's another product in there. We have to use the product rule again to get our final answer.
That's right, 2. We had to use the product rule twice, just for that one single third-order derivative. It's such a perfect example of how these higher-level concepts are really just built on making sure you've mastered the fundamentals.
And that really brings us to the big takeaway for today. Clairaut's theorem is an amazing tool. It's your friend, really. It tells you that for mixed partials, the order doesn't matter, and that can save you a ton of time and effort. But, and this is a big but, it's not a magic wand. You still have to be super careful with your fundamental derivative rules. You gotta nail that product rule, that chain rule, every single time.
So we've nailed down that fxy equals fyx. But that leaves us with one last question to chew on. What happens if we throw a third variable, z, into the mix? Do you think that f sub xyz would be the same as, say, f sub zyx? Or any other jumbled up order? Think about how the logic we just used might extend. It's a cool thing to ponder. Thanks for tuning in.